our lab on measurement of generalized constants ABCD of a long transmission line. Okay, so I'm sharing my screen. Before I share my screen, I want to say that you have to record the session because the recording facility has been withdrawn by Google. Okay, so I would not be able to record the session. So I would ask you all if any of you can record the session through screen recording or whatever, you may do so. Okay, you may do that. So let's start our class. Let me share my screen. Okay, it is visible. Is it visible?
Yes, sir, visual.
Yes, sir, visible.
Okay, so let's start our class. So as you can see that we are talking about measurement of generalized constants ABCD of a long transmission line. So what we'll be trying to do is that we'll be trying to measure the voltages and currents along the phase angle between them at two ends of a transmission line. We have a single transmission line. We were talking about the voltage and currents along with the phase angles between the voltage and the current at the two ends of a transmission line under open circuit and short circuit conditions, and to compute therefrom the ABCD constants of the transmission line on the test. So if you recollect, that is what we are doing is actually we are finding out the we are using the open circuit test and the short circuit test of the to find the ABCD constants of a long transmission line. Okay, of a long transmission line. As you know, that when you're talking about a transmission line, we can actually divide the transmission line into three parts, that is short line, medium line, and long transmission line. So what we can do is that generally the in term it is distinguished in terms of the length, and keeping in mind, so if we think in terms of the length, then we can actually define that the long transmission lines refers to those transmission lines which have length more than 240 kilometers. Okay, in theory it is 240 kilometers, but in real life it may be more. Okay, what happens is that actually this definition that we have talked about, that the short transmission line is up to 80 kilometer, from 80 to 240 it is medium, and from 240 onwards it is long transmission line. That depends upon, that is a very theoretical in the sense, because this may change from utility to utility. Okay, means the it may be the case for our WB ACTCL, but it may not be the same for any southern transmission company. Okay, located in the our southern part of India. So please remember, these lengths that we are talking about, these are very theoretical, but it will change. It may change if depending upon the utility. So if you recollect that for short transmission lines, the capacitance effect is quite negligible. Okay, whereas the capacitance of lines cannot be neglected for our medium transmission lines, and it may be considered to be lumped at one or more points of the line. Okay, whereas the capacitance is, we can think about that the three parameters that we're talking about, there is the R, L, and C, as well as we can take into account the shunt conductance. All these four parameters will be means all the effects of all these four parameters will be more sound in case of our long transmission lines. Okay, so in long transmission line, what we take into account, we take into account that the line parameters R, L, C, and G, that is the shunt conductance, are distributed uniformly. Okay, are distributed uniformly along the whole length of the line. So that's why what we do is that we consider a long transmission line to be consisting of large number of short sections. Okay, and what we try, and using this incremental length of the transmission line, we did find out the ABCD parameter of the transmission line, correct, in our power system planning and design classes. Yes, we have done that. Okay, So keeping in so in this class again, what we're doing will
Hello,
be
sir.
again.
Someone is trying to join.
Someone is trying to join. Where? Nobody is there.
But he has said in the group.
Nobody is here. As you can see in the screen, nobody is there. I think their internet connection may be an issue. Okay. Yes, as I was saying, that we have find out the ABC, means we did find out the ABCD parameters of a long transmission line in case of in our power system planning and design classes. So in this class, we'll be finding them again through the open circuit test and the short circuit test. Now, as you know that why we are using ABCD parameters, because we can think of a typical transmission line to be a two-port network where we have input and another part we have our output, correct? So if we think a typical transmission line to be a two-port network, then we can think of it that it is having a parameter which is known as our transmission parameters, also known as our ABCD parameters. Okay, so the transmission network is actually a bilateral network. Okay, why bilateral? Bilateral means that it can pass current equally well in both directions. Okay, so that is what we know as a bilateral network. We'll be seeing that the transmission network will be basically a reciprocal network. Means how we can say that it is a reciprocal network? Anybody? How we can say that the transmission network is a, or the transmission line is a reciprocal network? Anybody? By seeing that AD minus BC is equal to 1. Okay, by seeing that AD minus BC would be equal to 1. Okay, by seeing that we can actually see that that the circuit is reciprocal or not. Okay, and similarly, another important relation that we have to find is that A should be equal to D. That is, A parameter should be equal to the D parameter, and that will happen only if the network is symmetrical. Okay, so what do you mean by a network is symmetrical? It is symmetrical if means we can say that a network is symmetrical if it is electrically identical from either end. Okay, so for a symmetrical network, the input and the output terminals may be interchanged without affecting the network behavior. That is what we know by a symmetrical network. So what we'll be doing in our particular experiment, so we have a typical transmission line, as you can see. We'll be seeing the picture also. Okay, typical transmission line, and we have this our voltage source which will be providing while measuring the voltage and the current. We have a phase angle meter also. Please remember the switching function that has been shown in this circuit diagram in our experimental setup. We do not have any such switch. What we do is that we manually means we have to change the supply from one time we have to give the supply to the sending end, and at the other time we have to give the supply to the uh, our receiving end. Okay, so what we do, we manually change the supply from the sending end to the receiving end. So though there is a picture of a switch in our actual work, we do not use any switch. Okay, please remember this. um, okay, so what we have to do, so let us see. So we have to connect the circuit as shown in the figure, and we have to take the voltage signal as the reference, and we will be taking actually two voltages. One would be at 75 volt, another is at around 125 volt. The reason why we are taking two voltage values, because the inductors that we are using, they are very old. Okay, so they may have reached their saturation limit. So that's why we'll be taking one voltage at a very lower value, and and at a very higher value, that is at 125 volts, and another at 75 volts. So basically we'll be taking the of average of the impedance values for the two voltage cases, so that our mean or our average lies around the knee point of the inductor magnetization curve. Okay, so what we'll be doing, maybe we connect. So here in the run one, what we're doing, by connecting the sending end of transmission line to the supply, measure the sending end voltage, current, and the phase angle with proper sign, lag or lead that will be uh, provided by the phase angle meter. Between them, keeping the receiving end open. Okay, first of all, we'll keep the receiving end open. Okay, then calculate the mean value of impedance measured at two different values of the input voltage, as I was saying. Similarly, will be just changing. First of all, supply will be continuing at sending end, but first will be receiving end open, then would be receiving end short. Third run, what will be doing? We're connecting the receiving end. We're connecting the receiving end of the transmission line to the supply. Okay, and we're measuring the receiving end voltage, current, and phase angle between them, keeping the sending end open. And the second case will be keeping the sending end shorted. So we'll compute the ABCD parameters from the mean value of the impedances. Okay, and we can comment on the values of the ABCD as obtained. Okay, we'll be seeing what are the values are coming. Okay, so let us see then the yes, this is our PPT. So yes, this was our objective. This is a circuit diagram. Okay, so let's start with the procedure. Okay, let us start, or let us see the procedure. Just tell me if you can hear the video or not. Okay, this is the circuit diagram for. Is the video audible?
Yes, sir.
This is the circuit diagram for measurement of generalized constant of ABCD parameter of a. Okay, as you can see, so the figure that we have here, am I audible? Hello?
Yes,
Okay.
sir.
So as you can see here in the figure, so all the shunt or the leakage conductance, capacitor, and the resistor and the inductor are shown here. Okay, in the figure, and this is the panel actually, and behind this glass panel is actually what we have. We have all these capacitors and the inductors. Okay, so the whole thing is a six. Means all the connections are in T network, as you can see. Okay, we are using T networks here, and all the connections are in this T network. Okay, so let us see, continue. As you can see that these are the panel meters which is showing the voltage and the current that is flowing through this transmission line. These are all the inductors, the capacitors that is being present here. All can be seen from this small video. This is the phase angle meter by which we will be seeing how much phase lag or lead has occurred. As you can see, lead and lag has occurred, and this is the variac. And this is the circuit diagram of the circuit. Okay, please, I regret that the videos are very shaky, so please bear with me. Okay, so the first case, what we have a symmetrical case, means all the means there will be no change in the circuit. The circuit that you saw, that will be as it is. Okay, so let us see symmetrical case. Symmetrical case means, see, all these means all these are connected. So means all the circuits are connected. The supply is on the sending end side. So your right hand side actually is your sending end. Your left hand side is your receiving end. Okay. So first of all, what we are doing, we are, if you see the manual, we were the first of all the supply will be will be at the sending end of the transmission line and keeping the receiving end open. Okay, so first of all, we are keeping the receiving end open, and that is what we are seeing here. See, the receiving end is kept open, the supply is on the sending end side. As you can see, the supply is in the sending end. The supply is in the sending end, and we'll be measuring the voltages and currents, the supply at the sending end, and then we'll be measuring the impedances. What is happening? Okay. So next video. Okay. Now the voltage has been increased to 125 volts and the source is at the sending end with the receiving end open. And again, we'll be calculating the voltages and currents and with the proper phase angles, there is lag or lead, and we'll be measuring the impedances. Okay, as you all can see now, now what you can see that the sending end has been shorted and the supply has been sent to the receiving end. Okay. So voltage is being maintained at 75 volts with the supply given to the receiving end with the sending end shorted. Is it okay till now? Yes? Hello?
Yes, sir.
Okay. So what? So in the asymmetrical case, what we'll be doing? We'll be just removing one portion of the T circuit. So it will not be a symmetrical 6T network, rather a 5T network. Okay, but we can also say it as an asymmetrical 5T network. Okay. As you can see that we have now the voltage is at 75 volts and it is being applied at the sending end. But as you can carefully notice here that it is not a symmetrical case now. Now it is an asymmetrical case. Okay, one T connection has been removed. Okay. So after doing all these things, what we'll be doing, we'll be achieving certain impedance values. Okay. So these are the values that we are getting. So when first symmetrical module, voltage is taken as reference, sending end is the supply and receiving end open, sending end supply, receiving end short. Then we'll be just changing. That is the sending end open, receiving end supply, sending end short, and receiving end supply. For all the four cases, we are finding out the current values. Now, as you can see that whenever the receiving end is open, what is happening? That the phase angle meter is coming out to be lead. Anybody, why it is coming out to be leading? Why the phase angle is coming out to be lead when we are just when it is sending and supply receiving open? Capacitance effect. The actual term, what we can say, the term that we can say is known as anybody? Where the receiving end voltage or Ferranti effect, correct? Okay, as you can see that when we are talking about receiving end open, we can see that the current is leading in nature, whereas when it is receiving end is short, that the current is lagging in nature. Okay, so whenever the receiving end is open, because a transmission line, a long transmission line has a large capacitance, so if such a line is open circuited or in a very lightly loaded condition at the receiving end, the magnitude of the voltage at the receiving end becomes higher than the voltage at the sending end. Okay, and this phenomena is called the Ferranti effect. Okay, and we can say that the value of the current at the sending end at no load and normal operating voltage applied at the sending end is called the charging current. Okay, so how do we reduce the Ferranti effect? We obviously we want that the Ferranti effect should be less. Okay, and that's why we go for our shunt inductance. Okay, so whenever the voltage value is much higher, I have a figure on that one also. Oh, not here. Which one I did? No, not this one. Okay, I think I have misplaced this one. Okay, whatever be the case. So whenever we have a ferrite defect, what will happen? That we have a shunt inductor actually. Okay, so that what it will do, it will draw the excess amount of uh, var. It will draw the excess amount of reactive var from the system, so that the voltage at the receiving end goes to its nominal value. Okay, that is what we use, and that in that way we can actually uh, is control the voltage at the receiving end side. Okay, we can control the voltage at the receiving end side. Okay, so please, we are studying the power system performance also. So as we are studying the performance, power system performance, you will be seeing that uh, in the first class also, in my power system performance class, I said one thing, that the reactive power is strongly coupled with the voltage, and the active power is strongly coupled with our the load angle delta. So if we have to maintain the voltage at the prescribed values at all times, please remember that it is necessary to maintain the balance of the reactive power in the system. That is the reactive power generation should be exactly equal to the reactive power consumed or absorbed. Okay, so any mismatch of this reactive power balance will be affecting the bus voltage magnitude without affecting the system frequency. Okay, uh, and that's why what happens, that it is very difficult to maintain this reactive power balance because of the uh, unpredictable demands of the consumers, and because of which there is uh, means an unbalance always exists between the supply and the demand conditions of reactive power, and there is always a variation of voltages from their respective values. Okay, so what we do, that so we always try, please remember that we always use these inductive reactors, as I said, which may be connected in series or parallel with the network. Okay, so while these series reactors are actually used for limiting the fault current, these shunt reactors is used uh, for our reactive power control. Okay, so as I said, that whenever we have a lightly loaded condition in the transmission line circuit, so the shunt reactors are connected so that they may absorb the reactive power from the system, so that the voltage goes down to its nominal value. Okay, so in this our particular experiment, so when we are symmetrical 60 module, these are the voltage and the capacitors that we are means voltage and the current that we are seeing in the circuit. Similarly, we can also find for our asymmetrical module as the figure we saw. Okay, so কিভাবে আমরা দেখতে পাচ্ছি, so one capacitor is disconnected. So this is an asymmetrical 60 module. Here also we are seeing, we will be taking the voltage as the reference, and also we'll be seeing the phase angle for between the voltage and the current for each cases. So প্রত্যেক কটা কেসের জন্য দেখো আমরা দুটো ভোল্টেজ নিচ্ছি, as I said, one is at a low voltage 75 volts, and another one is at a high value, that is our mm, how much we are taking at around 125 volts. Okay, so what we have to do, we have to find out the impedances, and then we have to proceed to find out the ABCD parameters. Now the question comes that how we'll be proceeding. Okay, so as I said in the start of the class, that we can take, or we can think of the transmission line as a two-port network. Okay, so please remember that when we're talking about a two-port network, the general convention is that current is into the network, correct? But since we are talking about a transmission line, we can think of it in this way, that the current is means this is the input side and this is the output side, and that's why the current is, since we are considering it to be a transmission line, so the current direction will not be changing. Whereas in the convention of two-port networks, if both the currents is actually into the network. Okay, so since we are considering a transmission line, we can think that the current is and ir to be in this direction. So let us see that how, with respect to the impedances, we can find out the ABCD parameters. So we are going for short circuit and open circuit test, and how the impedance values will be helping us to find the values of ABCD parameters. So as you can see, what we can write? We can write Vs is equal to AVR plus BIR, and Is equal to CVR plus DIR. So the meters are on the sending end side. That is, on the sending end side, we have given the supply. Okay, sending end, the supply has been given. In this condition, when the receiving end is short, okay, when the receiving end is short, so VR would be equal to open, means the VR would be equal to 0, and our if this VR is 0, so putting the VR equal to 0 in this particular equation, okay, in this particular equation, what we are getting? We are getting, see, Vs equal to BIR, Is equal to DIR. Okay, so ZRS, that is receiving end short. ZRS equal to Vs by Is equal to B by D, where B equal to D into ZRS. Similarly, we have receiving end open. Receiving end open means our IR would be equal to 0. That is what we are having here, IR equal to 0. So putting IR equal to 0 in this equation, what we are getting? Vs equal to AVR, Is equal to CVR. So what we are getting? Zs or ZRO, that is the receiving end open, equal to Vs by Is, which is equal to A by C. So what is the equation that we are getting? We are getting A equal to C into ZRO. Okay. You have done this, no, in your power system planning and design classes? Yes? Okay. So now what will we doing? So we can write. So now what will be changing the direction of the meters? No. So meters are on the receiving end side, and as you can see, but though the meters are on the receiving end side, please note that the phase angle meter is measuring the will be measuring the current flow in this direction. Okay, as you can see that the means the current flow should have been in this direction, since meters on the sending end side, sorry, meters are on the receiving end side. So supply টা আমার এখানে আছে. Okay, the supply is present here, but the phase angle meter is measuring the current to be in this direction, as you can see. Okay, so this is the direction of IR in which the phase angle meter is measuring. Rather, the phase angle meter should have measured that the current is flowing into the network. Okay, and this is the other part. Okay, so as you can see, note here the direction of IR in the phase angle meter is just opposite of the original direction of IR. So therefore, a 180-degree angle should be added with the measured phase angle of impedances. That is, IR should be actually equal to minus IR. So when the meters are on the receiving end side, then how we can write the expression of our ABCD parameters? So as you can see, we can write VR IR equal to ABCD to the power means inverse Vs by Is. Okay, so from this expression, what we can write? We can write VR equal to dVs minus BIs, and IR equal to minus CVs plus AIS. Okay, so this is the equation. So when we are saying sending end short, okay, so in this condition, when sending end is short, so Vs would be equal to 0. So if we put Vs equal to 0 in this particular equation, we are getting VR equal to minus BIS and IR is equal to AIS. Okay, so sending end short, but that is ZSS, sending end short equal to minus V by R, which is equal to minus B by A. Okay, which is equal to minus B by A. So sending end short will be equal to how much? VR by IR angle minus phi R. Please note that this phi R is less than 90 degree, and this minus sign is going away because why? Because there is a 180-degree phase shift to be added with the value of IR. Okay, that's why what we are getting ZSS equal to B by A, not minus B by A. Understood why this negative sign is going away? Yes? Hello?
Sir, can you repeat again?
Okay. I'm again saying that when the meters are on the receiving end side, okay, when the meters are on the receiving end side, the phase angle meter is measuring the phase angle meter is not changing. Phase angle meter যে কানেকশন গুলো আছে, that is as it is. Okay, so that is not changing, so the phase angle meter should have measured that the current flow is in this direction. Okay, but it is measuring the current flow in this direction only. Okay, in the direction shown. Let me just yes, that is, it should have measured the current flow in this direction, but it is measuring the current flow in the previous direction only. Means it is measuring the current flow in this direction only. That's why the there should be a 180-degree phase shift. Okay, that should be added with the value of current IR. Okay, so now uh, what is VR by IR? So VR IR equal to ABCD inverse into VS by IS. So that expression comes out to be, then VR would be equal to dVS minus VIS, IR would be equal to minus CVS plus AIS. Okay, so when sending end is short, then VS would be equal to 0. VS equal to 0, we are applying into this equation. So VR would be equal to minus BIS, IR would be equal to A into IS. Okay, so Z SS, that is sending end short, is equal to minus of VR by IR equal to minus B by A. Okay, but we should not be taking this minus, because why? Because the IR is actually having a 180-degree phase shift. So that would be changed. So keeping that in mind, ZSS would be VR by IR angle minus phi R is equal to B by A. Okay, this phi R value, please note that that is less than 90-degree. Similarly, yes, it is clear now.
Yes, sir.
Okay. Now the sending end open, what will happen when we are talking about sending end open? Then IS would be equal to 0. Okay. So if IS is equal to 0, if we put in this equation, so VR equal to dVS, IR which will equal to minus CVS. So sending end open. So we have ZSO equal to minus VR by IR. So it would be minus D by C. Again, see, using the same logic that the IR should be equal to minus of IR. That is, actually there is a 180-degree phase shift. Using that one into consideration, what we are getting, ZSO equal to VR by IR angle phi R equal to D by C, where phi R is again less than 90-degree. Okay, so from this expression of 4, what we can write? We can write D equal to C into ZSO. Okay, now in our first equation, we did find out that B equal to D into ZRS. Okay, so what? So it in respect of D, what we can write then? We can write C into ZSO. So what we can write, B equal to D into ZRS, that is equal to C into ZSO into ZRS. Now what we know, that whatever be the case, the transmission line is a reciprocal network. Okay, that means it may be asymmetrical, it may be symmetrical, but whatever be the case, the transmission line will always be a reciprocal network. That is, AD minus BC should be equal to 1. Okay, so if that is what we are taking into account, so AD minus BC is equal to 1. So in place of A, we are writing what we are writing? We are writing this expression of 2A, that is C into ZRO. Okay, in place of D, we are writing C into ZSO, and in place of B, I am writing C into ZSO into ZRS. So it would be, this expression would be equal to 1. So keeping the C in common, what we are getting, 1 by root over of ZSO into ZRO minus ZRS. So from this expression, when we are getting the value of C, and from the value of C, we can easily calculate the other values. Okay, I have done one for you. Okay, so for symmetrical case, as you can see, for the values of A, B, C, and D, you can see that the value of A and D should have been equal, but obviously we are not taking into account all the losses that are actually occurring in the system. So keeping all the losses, if we take into account, so will be getting, in theory, A should have been equal to D for a symmetrical case, but we are getting them more or less equal, and AD minus BC should have been equal to 1 angle 0 degree, but here also we are getting the value to be more or less equal. Okay, yes, any questions till now? Any questions till now? Okay. Now what you have to do in the your lab report? You have to obviously write down the title objective circuit diagram as it is written, and in the result section also is been given to you. Okay, both for the symmetrical as for the asymmetrical case. In the report section, you have to calculate the values of the impedances. How? The way that I have shown here. So you have to find out the value of ZRS, ZRO, ZSS, ZSO, and you have to calculate the value of the C for both symmetrical and for asymmetrical case, and you have to find out the values of A, B, C, D parameters for both symmetrical and for asymmetrical case. And you will be seeing that in a symmetrical case A will be more or less equal to D, and in the asymmetrical case A should not be equal to D. Okay, and that's how you can differentiate between the symmetrical and the asymmetrical case. Okay, that is what is your report. And in the last part, obviously in the remarks section, you can write what you have understood from this particular uh, ABCD parameter experiment. Okay, any questions? Any questions? Yes, any questions?
Sir,
Bolo?
sir, for the reports, will we do both for symmetrical and asymmetrical?
Yes, yes, yes. Both symmetrical and asymmetrical has to be there in the report. Okay, both symmetrical and asymmetrical, all the impedances you have to calculate. That is for 75 volts ekbar 125 volts, they have to find out the mean value of them, and you have to find out the this ZRS, ZRO, ZSS, and ZSO, and the C parameters, A parameters, B parameter, and D parameter for both symmetrical and asymmetrical case. Okay, any more questions? Any more questions? If there is no more questions, then we are stopping the lab class here only. Okay, let me just stopping the presentation and let me take the attendance. Okay. So thank you everybody. I have taken the attendance. Okay, I have taken the attendance. So thank you everybody. Thank you for joining the class.
Thank you, sir.
Thank you, sir.
Okay, one thing. Please remember that the report you have to submit within 1 week. Okay, that is within next Tuesday. Okay, please submit the report within next Tuesday. Thank you everybody.